Welcome to join this talk. This work is about SNARGs for P from learning with arrows. I'm Zhengzhong Jain from Johns Hopkins University. This work is joined with Arka, Choudhuri, and Abhishek Jain. SNARGs refers to succinct non-interactive arguments. Such an argument is a two-party protocol between a prover and a verifier in the CRS model, where both parties hold some machine M and some input X. This machine M is a deterministic or non-deterministic Turing machine that takes the input X and outputs 1 within T steps. So the prover tries to convince the verifier the fact that M of X equals to 1 by sending a single round of message pi. Finally, the verifier can decide to accept or reject in time that is significantly less than T. We require several properties of this protocol. The completeness requires that for any machine M and the input X with M of X equals to 1, the honestly generated proof should always be accepted. On the other hand, if the machine M doesn't output 1 on the input X within T steps, then any cheating proof should always be rejected. From what assumptions can we build such SNARGs? Previously, there are both positive results and negative results on building SNARGs for general NP language. On the positive side, it's known how to build SNARGs for NP from random numerical model or knowledge type assumptions. On the negative side, by Gentry and Weeks, they show it's impossible to build SNARGs for NP from falsifiable assumptions, with the caveat that they require the protocol to be adaptive sound, and the soundness reduction is a black box reduction. This leaves the following open question. Can we hope to build SNARGs for some interesting subclass of NP from falsifiable assumption? So one interesting subclass of NP is the P class, which consists of all the polynomial time computation. So why SNARGs for P is an interesting problem? Consider the following scenario of computing delegation. Suppose there is some client who don't want to do some heavy computation on its own. So it delegates some Turing machine M with some input X to this cloud. The cloud runs this machine M on the input X in T steps, and it sends back the output, which is M of X, and it also attaches some short proof pi, proving this M of X is indeed computed correctly. In this way, the client only needs to verify this proof pi in time that is significantly less than T. It turns out that in this setting, the Gentry-Weeks impossibility result doesn't hold, and we can hope to construct SNARGs for P from falsifiable assumptions. A closely related subclass of NP is the batch NP. In this setting, the prover tries to convince the verifier that a batch of k instances from x1 to xk are all in some NP language L, still by sending a single round of message. Finally, the verifier can verify this proof in time that is only polynomial in the total length of the instance, plus some additional term that is only polylog in k. Batch verification is also very important and has been studied for many crypto primitives, such as signatures, interactive proofs, etc. And also in this setting, the Gentry-Weeks impossibility result also doesn't hold. Previously, we already know how to build SNARGs for P or batch NP in the designated verifier setting from standard assumptions. This follows from a long line of works. In this setting, the verifier needs to hold some secret key Sk corresponding to the CRS to verify the proof. However, in this work, our focus is on the publicly verifiable setting, and this setting is particularly interesting because anyone can verify the proof, and also the CRS is automatically reusable for different theorems, which is not the case for the designated verifier setting. For the publicly verifiable setting, we previously know how to build SNARGs for P or batch NP from less than assumptions. One line of work built SNARGs from I/O or multilinear maps. More recently, by the work of Kalai, Penance, and Young, they built SNARGs from new assumptions on bilinear maps. However, despite recent progress on basing I/O from well-founded assumptions, those assumptions are relatively less well understood. So in this work, we studied the following question. Do there exist SNARGs for P from standard assumptions? In fact, there are a lot of progress recently on this problem. For example, in a recent work by Joel et al., they built SNARGs for bounded depth computation from self-exponential learning with error assumption, which improves the strong assumption used by Kennedy et al. And both of these two works are based on the interactive delegation of bounded depth computation by Goldwasser et al. And here is our result. In this work, we construct the first SNARGs for P from learning with error assumption. Moreover, in our construction for t-time computation, our serialized size, proof size, and verification time are all only polylog in t. And to obtain our result, we also obtained the following result for SNARGs for batch NP. We built SNARGs for batch NP from K from learning with errors, and in our construction, if there are K instances and the NP relation can be verified in t time, then our serialized size proof size only grows polylog in K and t. To achieve our results, central to our method is the Fiat-Shamir paradigm. Next, I'm going to recall what's the Fiat-Shamir transformation. The Fiat-Shamir transformation is a method to round collapse a public core interactive protocol into a non-interactive protocol by replacing all the Wi-Fi's message with the hash of the transcript so far. And the soundness of the resulting protocol was firstly proven in the random oracle model. Later, a long line of research initiated by Kennedy et al. Started to instantiate this hash function in the standard mode. And the high-level idea to build such a hash function is that we want this hash function to behave like a random function. More specifically, we want its input and output pair doesn't satisfy any bad correlations. So the work by Kennedy et al. Further formalized this idea as correlation intractable hash. Such a hash function is in fact an ensemble of hashes that is indexed by some key k. Then we say this ensemble of hashes is correlation intractable for a relation class R if for any relation R in this relation class, and for any efficient adversary, given the adversary a key k sampled by some key Jain algorithm, we require that it's hard for this adversary to find an input x, such that the input and output pair corresponding to this x is in this relation R. Now, given this CI hash, how do we prove the soundness of the resulting protocol? The idea is to start with the interactive protocol and define some bad relation, which consists of all the pairs of alpha and beta, such that there exists some gamma that can make this transcript be accepted. Then one can argue that in the resulting non-interactive protocol, if the proof, which is the transcript of this sigma protocol, is accepted, then this means the pair of alpha and beta is in this bad relation. However, this contradicts to the correlation intractability, and in this way, one can prove the soundness. However, to make this argument really works, we need the initial protocol to be statistically sound. Because otherwise, this bad relation may be a trivial relation that consists of all the pairs of alpha and beta. And currently, we don't know how to build the CA hash for such relations. So it seems that we can only round collapse interactive proofs using the CA hash method. To obtain a SNARG, we need to round collapse succinct interactive proofs. So what's the previous works? Previously, it's known how to build such protocol for bounded depth computation by Goldwasser et al. In fact, This is how the work by Joel et al. And the work by Kennedy et al. Obtained their result for SNARGs for bounded depth computation. Another line of work constructed succinct interactive proofs for bounded space computation in P by Greengold et al. However, these works only deal with some subclasses of P, and the succinct interactive proofs for all of P are unlikely to exist. So it seems that we are stuck. To achieve our result, what is our method? Our method is the following dual-mode interactive arguments for batch NP. I will show you how to use the same idea to construct SNARGs for P later. For now, this interactive argument is an interactive protocol in the CRS model, where in the security proof, in the soundness proof, we will switch the CRS to a troubled mode, where the CRS in the troubled mode is associated with some index I, such that the same protocol becomes statistical sound for the ith instance xi, which means even unbounded cheating prover cannot cheat for the ith instance. Next, to obtain a SNARG, we will apply the Fiat-Shamir transformation using the CI hash method to this interactive argument. Now, how to prove the soundness? The key observation is that if the cheating is successful, then this batch of k instances from x1 to xk in language L doesn't hold, which means there must exist some index I such that xi is not in this language L. So in the soundness proof, we will switch the CRS to a troubled mode CRS that is associated with the ith instance. Then the protocol becomes statistical sound for xi. Next, we can apply the correlation intractability for the CI hash to prove the soundness. Now, I'm going to show you a super high-level overview about how we use the same idea to build SNARGs for P. At a high level, we have the prover to prepare all the intermediate state for each step of the computation in P. Then in the soundness proof, we will switch the CRS in the normal mode to a troubled mode that is associated with two adjacent states, such that the same protocol becomes statistical sound for one single step in this computation. Then we can argue that for these two particular states, these two states are computed correctly. Then we can switch the CRS in the troubled mode until we reach the final state. In this way, we can argue all the intermediate states are computed correctly. So we prove the soundness. Next, I'm going to show you more technical details. Instead of showing you how to build SNARGs for P, in this talk, I will only show you how to build SNARGs for bounded space computation. Since there is a generic transformation that allows you to go from bounded space computation to all of P. Our high-level idea is to use the SNARGs for batch NP to build such SNARGs for bounded space computation. Firstly, we have the prover to prepare all the intermediate states for this bounded space computation, and then we have the prover to send a SNARGs for batch NP language, which proves that for each step in this computation, the transition from the ith state to the ith plus 1 state is correct for each I. However, we cannot do this directly because the verification time is too large. If you look at the number of instances for these SNARGs for batch NP, there are T of instances. Recall that for SNARGs for batch NP, the verification time needs to be at least the number of instances, since the verifier needs to at least read all the T instances. In our case, we cannot afford this in our SNARGs for P, because otherwise the verification time will be at least T. To resolve this issue, our method is to use a commit and proof paradigm. So we first use some short commitment to commit all the intermediate states, and we require such commitment to have some succinct local opening properties. Such property allows you to open to some particular index in the committed string. And you can achieve this property by using the Merkle tree style commitment. Next, we will slightly modify the language for these SNARGs for batch NP. So additional to verify the computation from the IS state to IS+1 state is correct, we also verify there exists some local opening to these two states. Next, our key observation is that the instances for this language are just the indices themselves. They are integers from 1, 2, 3, etc. to t. So here, the verifier don't need to read all the instances. Instead, the verifier only needs to know this t to verify. So ideally, we can hope to build such SNARGs for batch NP language that only runs with verification time polylog in t. In this work, we formalize this idea as SNARGs for batch index language. We firstly define some index language, where it's just some normal NP language, but the instances are treated as index. And for such SNARGs for batch index language, the prover tries to convince the verifier that all the integers from 1, 2, etc. to t are all in this language L. And in this work, we build SNARGs for batch index language with verification time that is only polylog in t. So for now, let's assume we already have such SNARGs for batch index language. How do we prove the soundness? Our first idea is to use the soundness of SNARGs for batch index language. However, we cannot do this directly because the instance may be always true, since this commitment is a short commitment, and there might be multiple openings for any particular index I. So we need to use some statistical binding commitment. However, this is also impossible, since we also want this commitment to be short. So how do we achieve the succinctness for this commitment and also the statistical binding property at the same time? So the idea is to use an SSB commitment, which refers to somewhere statistical binding commitment. Such commitment scheme is also in the dual mode. It has a normal mode key, commitment key, and a trapdoor mode commitment key. So the trapdoor commitment key is associated with some subset of indices S, such that the commitment becomes statistical binding in the trapdoor mode for the indices in S. In this work, we further require there is an extraction property that allows you to extract the committed values in the subset S from this commitment. So with this SSB commitment, our initial attempt to prove the soundness is as follows. Firstly, we switch the SSB key to be statistical binding for the IS state to the IS+1 state. Then we can use the SNARGs for batch index language to argue that a single step of computation, the IS computation, is sound. Next, one may hope to switch the SSB key to be statistical binding for the IS+1 state and the IS+2 state, and further argue the computation at the IS+1 state is also correct. And maybe we can somehow combine these two correctness to obtain the correctness from the IS state to the IS+2 state. However, we cannot do this directly because the adversary may change the committed values. To resolve this, we need the following no-signaling SSB commitment. Such an SSB commitment further satisfies the following no-signaling property. It says that for any two subsets of indices S1 and S2, if you look at their intersection, then it satisfies that the extracted values at the intersection is indistinguishable for these two different keys. And by a recent work of Gonzalo et al., they show SSB implies no-signaling SSB. So how do we use this no-signaling property to argue the soundness? The idea is to switch the SSB key to be statistical binding for the first state and the second state. And then still we will use the soundness of SNARGs to argue the first step of the computation is correct. So in this way, we can argue the second step is computed correctly from the input X. Next, we will switch this no-signaling SSB key to be statistical binding for the second state and the third state. And the key step is we will argue that if before this key switching, the computation from the input to the second state is correct, then after this key switching, this property is preserved by using the no-signaling property. This is true because if you look at the intersection of these two subsets of indices, you will find that the intersection is the second state. And since whether the computation from the input to the second state is correct or not is an efficiently computable predicate, we can use the no-signaling property to argue that after this key switching, the computation from the input X to the second state is still correct. Next, again, we will use the soundness of SNARGs to argue the third step is still computed correctly from the second state. We continue doing this key switching until we reach the final state. In this way, we'll prove the soundness. Note that this proof strategy also works for non-deterministic bounded space computation. Thanks for watching. If you are interested, there are more details in our full paper online.